Hello. In these sections, we talk about the factor of the safety. Um, Here, there's two basic concepts involved. One is the definition of the factor of the safety. The second one is allowable stress. Both of the concepts are important, and both of the concepts will be used throughout these textbooks and will be used again and again in your future studies. So let's before we introduce the factors of the safety, let us look at okay. So the factor of the safety basically is allow designers to define or safety margin for his design. Before doing that one, let's take a look at the typical material properties. And by there, we're going to pick up one important term. It's called the ultimate stress, sigma U. Okay, and sigma U, ultimate stress. And this is a very important material properties. These properties can be done by applying we call the uni-axial loading. So here is the loading applied in the axial directions, and slowly, incrementally increase the magnitude of the force until the whole material is broken into two pieces. And the loading process, we can here divide the F by his original cross-sectional area to get the stress. And we can measure the deformation or displacement between the two points. And then from there, we can obtain what we call the strain, and which will be in detailed in chapter 2. Anyhow, the loading machines, they will record the loading history, and for certain material which is ductile material, for example low carbon steel, this loading behavior will be like this: initially increase linearly, to a certain point begin to down, and then gradually going up and to a certain maximum point, and then the curve going down. Here we record wherever the maximum stress occurred during the loading process is called the sigma U. U means ultimate. Okay. For the other type of the material, we call the brittle material, like aluminum alloy, like glass, and their loading features will be like this. Different from like this, it just monotonically increasing the stress until broken. So again, here we record the maximum stress occurred during the loading process, denoted as sigma U. And the sigma U is called the ultimate stress, which is a material property. Different material have a different sigma U. For this example, the low carbon steel, that is 60 KSI. For aluminum, and just by chance, also is equal to 60 PSI. Okay, so now we come to our definition factor of the safety. So here, this is the ultimate stress, and that is the maximum loading stress to break up a material. So in our design, of course we wish everything will be safe, so we don't want the material to be broken. So under these situations, based upon the material properties of the ultimate stress, we as engineers, we introduce a safety margin. A safety margin is defined through the factor of the safety. For example, if you define a factor of safety as 10, then your allowable stress equal to 60 divided by 10 equal to 6. So the allowable stress 6 KSI should be the maximum stress in your design that is allowed. Okay. For another example, if another engineer come to pick it up the factor of the safety equal to 5, so 60 divided by 5 equal to 12. So for the second engineer in that design, the allowable stress equal to 12. For example, some very rookie engineer, he would say pick factor of safety equal to 1. Under that situation, the allowable stress will be equal to 60 divided by 1 equal to 60. So under 3 scenarios, allowable stress equal to 6 compared to 12 compared to 60. And for the 60, that has the very narrow safety margin compared to 6, that corresponding to the factor of safety 10. That safety margin is kind of big. Okay. So that is the definition of the factors of the safety and in relation to allowable stress. So here, using this one, we introduce the 2 terms. Again, the ultimate stress divided by the factor of the safety, and that is your pick, and that will produce the allowable stress. And allowable stress is a design parameters. For example, using the carbon and low carbon fibers, we have the factor of safety 1, 2, 6, and allowable 60, 30, 10. Once the allowable stress is determined, which in terms depends on how you pick your factor of safety, then once this is determined, then the maximum stress, whatever the maximum stress happens in your design, must be less than this allowable stress to make sure everything is safe. Okay, so you may ask, for engineer A and for engineer B, for engineer C, they have a different pick. So which one is good? Here I can tell you, if you pick a factor of safety which is larger, then that means you give yourself larger the safety margin. That means because your design is more conservative, and in other explanation, your design basically is more bulky and a little bit wasting in will be more expensive in budget because you're going to use more materials to achieve certain design. On the other side, for one engineer, he picked only factor of safety equal to 1. For this case, the safety margin is very narrow. So basically, this is a very dangerous design. But on the other side, the budget for buying the amount of the material will be much cheaper than this one. Okay, so using these explanations, hopefully you have the common sense. The factor of the safety really have to compromise in terms of the safety and the budget. The larger the factor of the safety will lead to more conservative design, which in turn will require sometimes unnecessary more amount of the materials to accomplish that design. Okay. So we back to our previous example. Here, this is a strut carry a load 35 kilonewton, 30 kilonewton. That is our previous example here. Okay. So in that example, we have calculated the stress in here in bar BC. That is 159 MPa in magnitude. For example, if here we in our design we have determined the allowable stress is 165 MPa for bar BC. So again, what is allowable stress? allowable stress is such that the maximum stress should be always less than the allowable stress, which is design parameters. Okay, we'll look at this example here. So under this loading 30 kilonewtons, the corresponding stress is 159. For this case, the allowable equal to 165 MPa. So right now for the loading equal to 30 kilonewtons, the stress in BC equal to 159. Okay, so 159 is calculated due to the loading 30 kilonewton. That is less than allowable stress. So this loading is okay for this structure to carry on. On the other side, if say we try to risk the see what happens if the loading is increased from 30 to 35. Okay, we see what happens. So you can repeat the same calculations as we shown in the previous sections and give yourself an exercise at this moment. Okay, so when the loading changed to 35, then corresponding stress in BC will be up to 186. So when loading becomes 35 kilonewtons, the stress is 168. Okay, right now you can see this one is greater than allowable stress. So for this case, 35 kilonewtons be carried here, that will drive the stress here over the allowable stress. So is this okay to apply? No. So under this situation, you can say, based upon the determined allowable stress like this, then if we're going to use this structure to carry 35 kilonewton, this magnitude of loading is not okay, which means 35 kilonewton going to risk portion BC to fail. To fail, that means risk the BC to be broken, to be damaged. Okay, so that is the explanation of this. The design, one related design problems is this. If right now we change the material and from say the previous example using is steel, and right now we want to, for example, to save money, we want to change from steel to aluminum. Aluminum is always cheaper than steel, okay, not only in price but also in weight, lightweight. Okay, so that could be a good option. So we want to keep the dimension the same, but just simply change from steel to aluminum for part BC. And we look up the data book of the aluminum and from vendors, and the vendor provided the allowable stress is 100 MPa. So under these situations, we want to see if we swap this rod from steel to aluminum, would that be still okay to carry 30 kilonewton? The answer is, how do you think? Here we don't have this. Okay, we can recall. Okay, so from earlier our analysis, we have determined when the loading in kilonewtons equal to 30, as we showing here, the stress in BC MPa, and we've been calculated is 165. Okay, and our designed golden rule is this one must be less than or equal to the allowable stress. Okay, so right now for the allowable stress for aluminum, this one equal to 100 MPa. So compared to this one, you can see this one is greater than allowable. So this is not okay. Okay, so this design, if we're going to change from steel to aluminum, this one is not okay. So the follow-up question is this: if we want to make this okay, then how can we how do we modify the design? And the way to make the design is this. We're thinking that the stress in BC must be lower than or equal to the allowable stress. And this one is 100 MPa. Okay, and we know the stress we've been calculated, and we know in BC the loading equal to how much? I think is we can look at the previous slides. The BC. Okay, in BC that magnitude equal to in BC the magnitude equal to 50. Okay, so we come back to our slides here. So the magnitude equal to 50 kilonewton. So 50 times 10 to the 3 Newton, and divided by the cross-sectional area pi times d and 4 over pi d square. So using these situations, this one 50,000 Newton divided by pi over 4 d square, and say millimeter square must be less than equal to 100 MPa. Okay, so this is MPa, this is MPa, we can cancel out. So from here you can see 50,000 divided by 100 less than equal to pi over 4 d square. So by solving this one, you can determine the minimum from here. Let me do the quick calculations. So the 50 divided by pi and multiply 4